approaches to solve the problem, right? Because some problems you may approach, the same problem in different ways, you will get the same answer. So you are welcome to try other ways as well, right? If you get a different answer, or if you don't agree with the solution which I give, you are welcome to discuss with me, okay? What I'm trying to say is that your knowledge and the effort should not be confined to only my solution, okay? This, I believe, is the best solution or the right way or the easiest way, but there could be other easier way of solving this, okay? Problem number 1, it's designed to stream an uncompressed video at full HD, is high definition, resolution of 1920 by 1080 pixels. I believe you are all familiar with these numbers, okay? With 30 FPS, FPS stands for frames per second. How much data rate or bandwidth is required for this purpose? So the problem is we want to stream a video, but note it is an uncompressed video, okay? Most of the videos which we are watching are compressed, okay? It's an uncompressed video. So this problem I give you to appreciate the need for compression, okay? Why the videos are compressed, okay? If it is not compressed, how much data rate we need? This is the resolution, okay? When we say resolution, that basically represents the pixels which are arranged as in the matrix form, okay? So this is a picture frame, okay? Because a video is made up of a sequence of frames. We need to play the frames at certain rate. In 1 second, how many frames are played on the screen or monitor, okay? So that would define the quality, okay, of our viewing and other things. So this is comprised of a number of pixels which are arranged in multiple rows and columns. So each dot, so this, let's say call it as a dot. This is nothing but a pixel. A pixel means it's a picture element, okay? And what we do in the network or the computer context is that one frame is represented as a matrix of pixels, and each associated with each pixel there's a number, there's a binary number. We associate a number. That number represents the color intensity of that particular dot or pixel, okay? So how many different colors we can generate? In order to represent one dot, we use a mix of 3 colors, RGB. So these are the universal or basic colors, RGB. So when you mix up with a different combination, you can generate so many colors, okay? So theoretically, you can generate infinite number of colors, okay? That's used in monitor as well as TV, etc. So combination of RGB, okay? So the convention is that each of these colors is represented as 1 byte. That means red, to represent the red intensity in the mixture, we use a number from 0 to 255. 0 may be the 0, the dark, okay? 255 may be the bright, the brightest possible, okay? Similarly, green, we need another 8 bits, blue, another 8 bits. So in total, we need 24 bits to represent one dot, okay? So to represent one picture frame, we need this many bits. This is the number of dots, 24 is the number of bits needed to represent one dot. But how many such frames need to be played for us, okay, to play it as a video, right? So this problem says 30. 30 is not a very fantastic number, but it's a reasonably good number. But if you increase the 60 and all, okay, maybe if you look at your phone specification and all, that will tell, okay, 30 FPS, 60 FPS, right? So higher the numbers, the better the video quality which you can perceive, okay? So when you multiply all this, you get 1.5 Gbps, approximately 1.5 Gbps, okay? So now you can understand why, okay, we don't prefer to send an uncompressed video, okay? So we need huge bandwidth. But most of the videos which we watch on TV or phone and all, even with 5 Mbps, you will get one of the best quality videos, okay? Maybe 2 to 5 Mbps. That's what normally we use after compression, okay? But otherwise, it could be very difficult. Bandwidth is still inexpensive. So we cannot provide For single video streaming, this much bandwidth. Okay? But for medical image kind of applications where you store medical images or transmit and store maybe in a remote cloud or something, we may prefer still uncompressed images, right, which may need more bandwidth. Problem number 2, suppose a 100 Mbps link is being set up between Earth and a new lunar colony. The distance from the moon to the Earth is approximately 385,000 kilometers. And data travels over the link connecting the Earth and the moon at the speed of 3 times 10 raised to the power 8 meters per second, because this is the magic number which we know from our school, right? The speed of light in the ideal speed of the light, right, in free space. A camera on the lunar base takes pictures of the Earth and saves them in digital format remotely. Now, the mission control on the Earth, there's a mission control station at the Earth. Okay, so that wish to download the most current image from the moon, assume that the image size is 25 MB. The question is, what is the minimum time needed, okay, between when the request for the data goes out and the transfer is completed? Also calculate the effective throughput for the above case. So this question is quite simple. So let's say this is E, this is lunar colony, M, right? And there's a request sent from Earth to the lunar colony, and this in turn sends the image. Send the image. Okay? Assume that the request message is very short, because the request is not a big data like image and all, right? So in that case, you can ignore the transmission time of the request, then that means it needs only the propagation time to travel for the request message to travel from the Earth to the lunar colony, right? Because that distance is quite long. Compared to that, the transmission time of very short request message is very short, which is negligible, that we can assume, because we are not given anything about the request message size, etc. But the image size is given, this is 25 MB. Once the request is received, that is after TP, from the lunar colony, the message is being transmitted. It starts its transmission, okay, bit 0, bit 1, bit 2, bit 3. So how long it will take to transmit? That is TT time units. So at time TT, that is transmission time, the last bit of the image is transmitted at the lunar colony. And that last bit should travel towards the Earth. So that takes another TP time units. Is that okay? When the last bit is received by the mission control on the Earth, that implies all the previous bits have already been received, right? The bits are traveling one by one, right? So we look at only the last bit. That would be easier. You can also solve this from the perspective of the first bit. You should get the same answer, okay? So the total time elapsed is TP plus TT plus TP, that is TT plus 2TP, okay? 2TP, okay. What is the TT? Is the transmission time, size divided by data rate. Size 25 MB. When you say 25 MB, this is 25 by 1024 by 1024, because M, when you represent the size, it is 2 raised to the power 20. It is not 10 power 6. Okay? Multiplied by 8, so you'll get 2.097 seconds. That's the time required to transmit the image. TP, propagation time. So how do you find the time? That is the distance divided by the velocity or speed. The distance is given, speed is given, 1.283 seconds. So for the bit reaches the moon or Earth in 1.2 seconds. So we cannot reach, right? Okay. Now, when you add everything, you get 4.663 seconds. So that means you start the time when the request is sent. Within 4.663 seconds, the request will go and reach the lunar colony, and the image will get transmitted. You'll get the entire image down. within 4.6 seconds. Now the second part of this question is to calculate the throughput. Throughput is the ratio between the message size and the message transfer time, how long it takes to transfer the given message of a given size. So that gives 44.974 Mbps. That is about 45 Mbps. Note that the data rate or the bandwidth is 100 Mbps, but what we achieve, the throughput is only 45 Mbps. So that means the throughput rate is about approximately 45%. So throughput rate is the ratio between throughput and data rate. How close is the throughput to the bandwidth or data rate? Any doubt? Students, any doubt? Problem number 3. How many 10 Mbps inputs can be multiplexed onto 100 Mbps output? So let's say we have a multiplexer. It's a multiplexer. We have a number of 10 Mbps input links, and there is an output link whose data rate is 100 Mbps. That means the data which arrive at these inputs, they want to leave through this output link. They are all contending for this output link. Okay. The question is, how many 10 Mbps can be supported if fixed TDM is used? If fixed TDM is used, we need to guarantee 10 Mbps of bandwidth for each of the input on the output link. Okay. So that means that at most 10 Mbps, 10 inputs can be multiplexed. You cannot add more than 10 inputs. Okay. So then at the output you cannot guarantee the slots, you cannot schedule it. Is that fine? So if there is any request for 11th input or something, that would be rejected. That cannot be supported. Okay. But in the case of statistical time division multiplexing, which is based on the demand on average, there's no limit on how many 10 Mbps can be supported, or can be multiplexed onto 100 Mbps link. You can have 10 input ports or 20 input ports, 100 input ports, doesn't matter. Okay? Because statistical TDM, it uses a buffer, right? So whenever a packet is received, that is put in the buffer. And the packets will be sent to the output one by one. Okay? If the sum of the input data rate exceeds the output data rate, there will be excess number of bits or packets. Those packets will be waiting in the queue. The queue will build up. If the buffer overflows, there is a possibility of congestion. Okay? So how many inputs can be supported? It depends on how active the inputs are. So if you know that average only 10% of the time, okay, each of the input is active, they are actively transmitting, okay, then we can support 100 inputs. I mean, just an approximate value. Right? Problem number 4. A 20 kilometer long link is able to hold only 100 bits in one direction. What's the bandwidth of the link? Assume that propagation speed on the link is 2 times 10 raised to the power 8 meters per second. Because this is not the free space, okay? So usually inside the cable link, so the speed is reduced. Okay? Now, if you can recall the lecture notes 2, we have studied something like dB product. dB, delay. Delay is basically the propagation time. This is the bandwidth. Okay? So multiplication of dB product tells us how many bits are there in transit on the link. That is, when one bit signal is reaching here, there are many bits of signal they are traveling here, they are propagating here. Okay? So this is a quite straightforward application of the formula. Number of bits that can be held on the link is equal to delay multiplied by bandwidth. So the question, okay, out of these three, 2 values are given and the third value is asked. So bandwidth equal to number of bits divided by propagation time. Number of bits is 100, that is given, and the propagation time is nothing but the distance divided by speed. That's the time. Okay, that we know, we studied from the school, right? So that is 1 Mbps. The bandwidth of the given link is 1 Mbps. Okay, so this equation involves 3 variables. I think the school you might have studied the triangular formula, right? If 2 are given, the third one you can easily calculate. Problem number 5. It's a bit more interesting or more complex or a more interesting problem. A drawback of a broadcast network is that the capacity is wasted, that is bandwidth is wasted, due to multiple hosts attempting to access the channel at the same time. That's a broadcast network. So symbolically we represent like this. So many hosts are connected to this. Okay. Assume that there are n hosts or n systems connected to this. That means n systems that share this link. Okay. And assume that time is slotted for simplicity. Okay. So because we are trying to get some insights of how bad it would be if many are trying to transmit at the same time. Okay. Assume that each host attempts to use the channel with probability P during each slot. At a given time during a slot, let's say everybody is trying to transmit with probability P. Okay. So what does it mean? Okay. It doesn't mean that everybody is transmitting at the same time, right? So according to some probability, they are transmitting. So on one extreme end, if P is equal to 1, that means every time everyone will be trying to transmit, right? There will be collision. Always there will be collision, right? So bandwidth waste would be 100%. We cannot come back from the collision, correct? But if P equal to 0, that means no one is active. Nobody is trying to send anything. All the computers are idle, okay? Systems are idle, okay? And maybe it's a holiday or people have gone to watch some other sports or something, so everything is idle, okay, in the network. So if P equal to 0, that means no one is attempting. Again, bandwidth is wasted. Again, bandwidth is wasted, but here bandwidth is wasted because there is no demand. There is no demand. Nobody wants to use. But in between, that means if P is greater than 0, okay, then there is a possibility of collision. Okay, when there is a collision, okay, when 2 or more hosts attempt to transmit at the same time, then that will lead to collision, right? So that's a small probability that only one is trying to transmit in a given slot, right? Similarly, there's a small probability that nobody is trying to transmit. I should not say small probability, okay? There is some probability that exactly one is trying to transmit. If exactly one is trying to transmit in a given slot, there is no problem, there is no collision, okay? So if, let's say more than one, that means there is a probability that 2 people are trying to transmit at the same time. It has some probability associated with that. That's a chance. Similarly, there's a probability that 3 are trying to transmit, 4 are trying to transmit. Okay? So the question here is, what fraction of the slots is wasted due to collision? Note that bandwidth may be wasted because of collision, or bandwidth may be wasted because no demand. Nobody is trying to send. But we want to know the chance or fraction or probability, both are equal in terms, okay, of wastage because of collisions. So to solve this, we use what is called binomial probability. I believe you are all familiar with this, must have studied in the school itself, very simple probability. So binomial probability tells this. It's a probability of exactly r successes out of n trials. Assume that P is the success probability. What is the chance or what is the probability that, okay, out of n trials, you get exactly R successes. Maybe we can take the classical example of tossing the coin. Okay, when you toss the coin, P is 1/2. Let's say we are interested to get the head. Okay, interested to get the head, P is 1/2, right? Let's say you toss the coin n number of times. There's a probability that you don't get head at all out of n tossing, right? There's a small chance. There's a probability that you get head all the time, all n times. Every time you toss, you get the head. There's a small chance. Similarly, there's a chance or probability that out of n you get exactly one head, the remaining are tail. Okay. Similarly, 2 head, the remaining are tails, right? 3 heads plus the remaining tails. So these are different combinations, right? So what is the probability that out of n tosses or trials, you get R successes? Okay, R is less than or equal to n. So that is NCR, because that R can be any R. It need not be first 1, 2, 3, 4, or any R, right? Any place. So it's a combination. NCR multiplied by P raised to the power R. Okay, because P times it should succeed. Sorry, R times it should succeed. Okay, success probability is P. We should succeed R times. So P multiplied by P multiplied by P R times. So that is P raised to the power R. It is exactly R time. You should get exactly, let's say, 3 head. The remaining should be tail, right? So exactly R times you should succeed. That means the remaining trials you should fail. How many are remaining? N minus R. Out of n trials, R success, n minus R failures. That's what it means. So what's the probability for failure? 1 minus P. So 1 minus P multiplied by 1 minus P multiplied by 1 minus P, n minus R times, so raised to the power n minus R. Okay? So this is the binomial probability. We are making use of this to solve this problem. So in this case, P is the probability that a host attempts to use a channel in a slot. Let's say n number of hosts are trying to share the channel. Okay? And P is the probability that a host attempts to use it. That's a success probability. Okay? Now, Q0, let's use this to denote probability that no host attempts to use the channel in a slot. What's the probability that no one is trying to transmit? Nobody has data to transmit. That's what it means. So B n comma 0. Okay? Similarly, B n comma 1, let's denote it as Q1, is the probability that exactly 1 is trying to send. That means all the remaining n minus 1 are not trying to send. They don't have data or they defer sending the data. Okay? So that is B n comma 1. Right? Now we are interested in Q, the fraction of bandwidth wasted due to collision, or the chance or the probability that a collision can occur. That's what it means. So that BQ is nothing but B n comma 2. That is, what's the chance that exactly 2 are trying? What is the chance that exactly 3 are trying to send? Then 4, 5, n. In all these cases, there will be collision. Am I right? If 2 try to send with this probability, okay, or exactly 3, exactly 4, exactly 5, they are mutually exclusive because it's exactly 2, exactly 3, exactly 4. They are mutually exclusive. You can add. Still, probability will be within 1, right? So we are interested to calculate this, but that would be very difficult for us to calculate using this formula, what is Bn2, Bn3, Bn, etc. But we know that Bn comma 0 plus Bn comma 1 plus Bn comma 2, Bn comma n equal to 1, right? They are all mutually exclusive, right? So to calculate this, we use a shortcut method. This is nothing but 1 minus Q0 plus Q1. 1 minus Q0 plus Q1. So Q0, what is Q0? Q0 is B n comma 0. That's equal to NC0 P comma 0, 1 minus P n minus 0. So NC0 is 1, P raised to the power 0 is 1, 1 minus p power n is 1 minus p power n, this one. Similarly, b n comma 1 is nc1 p raised to the power 1 minus p n minus 1. nc1 is n, p raised to the power 1 is p, 1 minus p n minus 1 is this. That's all. So this is the answer. Any doubt? Problem number 6. Calculate the total time needed to transfer 100 kilobytes file in the following cases. Assuming an RTT of 100 millisecond, a packet size of 1 kilobytes of data, and an initial 2 RTT of handshaking before the data is sent. So note the following. 1. You are given an RTT, so implicitly it means it's a acknowledged transfer. It doesn't say the transfer is acknowledged, but when the problem talks about RTT, that means it's round trip time, so which is usually discussed in the context of acknowledgement. Okay. Now, one packet size is 1 kilobytes. The total total message size is 100 kilobytes. Okay. So how many packets would be there? 1,000 packets, right? So we need to send 1,000 packets. Okay. Now, question number A. The bandwidth or data rate is 1.5 Mbps. Data packets are sent continuously, back to back. That is packet 1, packet 2, packet 3, packet 4. Okay? It doesn't wait for any acknowledgement. Okay? So meaning is that because it talks about RTT, the acknowledgement is only at the end. Acknowledgement is happening only at the end. So maybe I use a timing diagram. So, that would help you to better understand how it works. So I always ask the students to draw the diagram to quickly understand it. Right? So it says there is an initial handshaking of 2 RTT delay. It does not send the data immediately, but 2 RTT, initially there is a delay of 2 RTT. Okay? So that happens because maybe the sender wants to say, hi, I want to send something, are you ready? Okay? Maybe the other party will say, okay, I am ready. Okay, you send it. Okay, these are the parameters, some parameters, you use it, something like that. Okay. So you'll study more about this initial handshaking and other things in TCP context, but usually there will be initial handshaking. So let's not worry about what is that handshaking. Handshaking means they mutually agree they are ready for transfer. So that takes 2 RTT. So this is the time for handshaking. Now the first packet is sent. The time to send the first packet is TT, second packet, third packet, fourth packet, and this is the packet 1000. Okay. Because there are 1000 packets. It is given. And after the 1000 packet is sent, here, this is the time when the last packet is sent. This is the time when the last bit of the last packet is sent. Just remember the terminology. When I say last packet is sent, it's not that the packet is thrown like this. Okay? The last bit of the last packet is sent here. And that last bit should travel to reach the other side. That needs TP time unit. Okay? And the receiver will send an acknowledgement. It doesn't say anything about the acknowledgement size, so you can assume that the transmission time of the acknowledgement is negligible. So it takes another TP time for the acknowledgement to come back. So at the end you have 2 TP. 2 TP is RTT. So as a result, there's initially 2 RTT. Finally, there's 1 RTT. In between, there are 1000 packet transmissions. Each packet transmission time is 5.461. How we get it? Because packet size is 1 KB, the data rate is 1.5 Mbps. Again, 1 KB is 1024 multiplied by 8. It's not 1000. 1 KB is not 1000 bytes. It is 2 raised to the power 10 bytes. Okay, 1024 bytes. Any doubt? Students, any doubt? Yes? Now let's look at a more complex one, or more complex or easier one, I don't know. Bandwidth is 1.5 Mbps, but After we finish sending each data packet, we must wait one RTT before sending the next. That means here you are sending the packets back to back. The sender sends first packet, doesn't wait for any acknowledgement or anything, second packet, third packet. Because it talks about RTT, we implicitly assume the acknowledgement comes only at the end. Okay? Now, in this case, look at this diagram, the timing diagram, how the transmission takes place. Initially, there is a handshaking delay of 2 RTT, this one. This is handshaking. Now, packet number 1 is sent. According to the problem, there is a delay of 1 RTT. Why there is a delay of 1 RTT? Before it sends the next packet, very easy to understand, okay? Because this is the time the first bit of packet 1 is sent. This is the time when the last bit of packet number 1 is sent. That last bit should travel to reach the other side. It takes TP time units for the last bit of P1 to reach the receiver, and the receiver will send an acknowledgement. That takes another TP time units for the acknowledgement come back. When the acknowledgement for packet 1 comes back to the sender will send packet number 2. That's why there's a delay of 2 TP, that is 1 RTT. So that happens for every packet transmission. So after P2, there's a delay of RTT. P3, P4, then P1000, then there's a delay of RTT. Now if you add everything, initially there's 2 RTT. Okay? Then there are 1000 packet transmission times. Then after each packet transmission, you can see 1 RTT, RTT1, RTT2, 3, 4, RTT 1000. So 1000 RTTs. RTT is given, that is 100 millisecond. Packet transmission time, we have already calculated. So now you add everything, you get 105.6 seconds. Got it? Any doubt? Yes? This follows some flow control protocol which we will discuss later. You will understand, okay? At that time, okay, why there's a need for such a time gap of RTT for every packet transmission. The last question is the most interesting question, and many times students get confused this question. But this question helps you to better understand what is transmission time, what is propagation time, what is transfer time. Okay, so these are all 3 different time quantities. Don't get confused. Transmission time is different from transfer time. Okay? This has 3 parts, A, B, C. So let's start with A. Okay? Calculate the latency. Latency is nothing but transfer time. Message latency or message transfer time, both are same. Okay? From the first bit sent to last bit received, I calculate the time, the transfer time, as the time from first bit sent, when the first bit is sent, and when the last bit is received. So I am not talking about the acknowledgement here, okay? If the problem mentions about RTT or I explicitly say it's an acknowledged transfer, then you can worry about the acknowledgement, otherwise don't need to worry about it, okay? A packet of 5000 bits is sent over 100 Mbps Ethernet from node A to node B through 4 store and forward switches in the path as shown in the figure below. Assume that each link introduces a propagation delay of 10 microseconds and the switch begins retransmitting immediately after it has finished receiving the packet. So the terminologies are very important. There is only one packet. The size is 5000 bits. And it starts from host A, ends at host received by host B. In between, it traverses switch 1, 2, 3, 4. And these switches are store and forward switches. So by default, the switches like routers or IP routers or Ethernet switches, they are store and forward switches. Switching means how you are forwarding an input data to it's the process of forwarding an input data, that is data received on an input port or inputting to the output link, that is switching, right? Store and forward means it is used in the context of statistical TDM. The entire packet must be received and stored, only then it will start transmitting on the output link. That means if the packet size is 5000 bits, the switch should receive all 5000 bits before it starts transmitting bit number 1 on the output link. It's not that it received some, let's say 1000 bits, then immediately it tries to send it to the output link. No, that's not store and forward, right? It is stored in the local buffer, then forwarded. Now propagation time on each link is 10 microsecond. The same propagation time that makes our calculation easier. And the switch begins retransmitting immediately after it finished receiving the packet. That means once the packet is received, once the last bit of the packet, the 5000 bits are received, it doesn't wait. There's no queuing time. That's what it says. It doesn't wait. It starts transmitting bit number 1, 2, 3, etc. Now, what is packet transmission time? Size is 5000. Data rate is 10 Mbps. So 5000 divided by 10 Mbps gives 500 microsecond. 500 microsecond. Propagation time is given 10 microsecond. Now you just imagine how the entire thing works. You look at the last bit of the packet. I always tell the student, look at the last bit. Because when the last bit is received, we say the transfer is complete. If you look at only first bit, again you can end up with the same answer, but after receiving the first bit, still you should add the quantity to receive the remaining bits, right? So better you look at the last bit. The last bit is transmitted at host A at time TT. Agreed? Packet transmission time is size divided by bandwidth, 500 microsecond. That means it transmits bit 1, bit 2, bit 3, bit 5000. According to the definition, as per the definition, bit 5000 is transmitted at time TT. That last bit should travel to reach the other side of the link, that is switch 1. Okay? So the last bit will take TP time units to reach switch 1. That means at switch 1, okay, the last bit is received at time TT plus TP. TT is the time when the last bit is transmitted. That last bit should travel to reach the other side. It takes TP time units. So TT plus TP is the time when the last bit is received at switch 1. When the last bit is received, automatically the previous bits have already been received. They are time overlapping. You should not add every bit time, right? Just look at only the last bit, okay? Now, after this TTTP, when the last bit is received, the switch will start transmitting on the next link. So again, it will transmit bit 1, bit 2, bit 3, bit 5000. So it takes another TT to transmit 5000 bits. And again, that 5000 bit, the last bit will be transmitted at time TT. That last bit will travel. It takes TP to reach S2. Only after receiving the last bit, S2 will start transmitting on the next link. So this will continue. Okay? So now you need to add all the time to get the transfer time. 1, 2, 3, 4, 5 TT, 5 TP. So when you add everything, you get 2.5 milliseconds. Any doubt? Students, any doubt? Okay, now we are going to look at a more interesting problem. Same problem, but the 5000 bits are sent in 5 packets, 5 small packets. Each packet carrying 1000 bits. Now we don't want to send 5000 bits as a single packet. This is small packets. Again, the question is how to calculate or what is the transfer time. Now the packet transmission time is, because the packet is smaller or shorter, 1000 divided by 10, that is 100 microsecond. Note that these switches are store and forward switches. They wait for the entire packet to be received before they start transmitting the first bit on the next link. If the packet size is big, let's say 5,000 bits, it has to wait for 5,000 bits to be received. Only then it can start transmitting the first bit. But if the packet size is small, let's say 1,000 bits, it will wait only for the 1,000 bits. Because as far as it's concerned, the packet size is 1,000 bits. The packet is done. Then it will start transmitting. So we expect that transfer time is faster or shorter. Okay? Now, how it works. You look at host A. You need to start the timer t equal to 0 when the first bit of the first packet starts transmission, right? The transfer time means you should start the timer when the first bit of the first packet starts its transmission. Okay? So host A will transmit the first packet, TT, second packet, third packet, fourth packet, fifth packet. The fifth packet is transmitted at time 5 TT. That means last bit of the last packet is transmitted at 5 TT. And all these packets or the bits will be traveling here one by one. When the last bit of the last packet received here, when it will be received? 5 TT plus TP, because that last bit has to travel, right? It takes TP 10 minutes. After 5 TT plus TP, the last bit of the last packet, that is fifth packet, is received at switch 1. Okay? When the last packet is received, what about the previous packets? Will it store all the previous 4 packets here? No, because as soon as it receives the first packet, it will send the first packet on the next link, okay? Because it doesn't know that 5,000 bit packet is divided into small packets, no. For it received one packet of size 1,000 bits. After receiving the first packet, it will start transmitting on the next link. That means when the second packet is received, first packet is transmitted here. When the third packet is received, second packet is transmitted. When the fifth packet is received, the fourth packet is done. They are all concurrent, simultaneous, okay? That's right. So the additional delay for switch 1 is it has to transmit now only the last packet. The previous packets have already been sent out. Within this time, 5 TT plus TP, within that time, 4 packets were already sent out. So it adds only 1 TT extra. Is that clear? So the similar argument holds. After TP, the last bit of the last packet is received here. Then again, it adds another TT for the last packet transmission. Similarly, this continues. So if you put all together, 5 TT here, this one, then 1, 2, 3, 4, 4 TT, then 5 into 10, 5 propagation time. You get 950 microsecond. So earlier it was 2.55 millisecond. Now it is 950 microsecond only. That means if you send a small packet, you get some benefit. The transfer is faster. Is that okay? But now we can ask this question, why I should send as 1000 bit packet, why not 500 bit packet? You make calculation, the time gets reduced. It will be smaller than 950. Then somebody may ask, why? No, I'll send it as 100 bit packet, right? If you calculate the time will become smaller. Then, on the other extreme end, can we send just 1 bit packet? Instead of sending 5,000 bits in one packet, why not we send 1 bit packet? There will be 5,000 packets, each carrying 1 bit. If you make the calculation, time will be shorter, still smaller, right? But that's fine, but conveniently we ignored something here, right? That means each packet carries header. Each packet carries header. So here we assume that 5,000 bit divided into 5 packets means, okay, each packet will carry only 1,000 bits. No. Okay, each packet will carry some extra bits, header bits. That part we omitted here. But still, even if you include header, the time will get reduced to some extent. But beyond certain size, the header will dominate. Right? So that problem we will discuss in tutorial 2. So we will wait for one more week. Problem number 7, the last part. Okay? Now, we use the same setup, that is, we are, it is same as A. That means we are sending 5000 bit packet, just one packet, but the switch is not a store and forward switch, but it's a cut-through switch. It's a cut-through switch. Cut-through switch means the switch does not wait for the entire packet to be received. The cut-through switch will wait for first few bits to be received, then it makes a decision, because usually the first few bits or few bytes, the first few bits or bytes are header bytes. That will give sufficient information. Okay, what is the destination address, etc. So based on that information, it can make a decision. It can make a decision to go to this link or this link. Okay. So now the question is why it should wait for the entire packet to be received. Okay, it has enough information. Send it. Before you receive the entire packet, you start sending. So according to this problem, it begins retransmit the packet on the next link after receiving first 200 bits. That means within 200 bits, the header carries sufficient information for it to make a decision. That's what it means. Is that okay? That means if this is the switch, when it receives bit number 201, it starts transmitting bit number 1. In the previous case, only after it receives 5000 bits, only then it can transmit bit number 1 on the output link. But here, when it waits for the first 200 bits. When it receives 201, bit number 201, it transmits B1 simultaneously here. Similarly, when bit 202 is received, bit 2 is sent here. When bit 5000, that is when the last bit is received, this would transmit bit 4800, correct? When bit 201 is received, bit 1 is sent. Bit 202 is received, bit 2 is sent. When bit 5000 is received, bit 4800 is sent. They are all simultaneous, concurrent. So that means after we receive the last bit, that is 5000, bit number 5000, the switch has to transmit how many more bits? It has to transmit only 200 more bits. The additional delay is only because of the transmission of these extra 200 bits. So the time to transmit 200 bits, let's call it as T200, that will be 200 bits divided by bandwidth. So that means when it receives the last bit, it needs only 20 microseconds to transmit the remaining 200 bits because it has already transmitted 4800 bits on the output link. Now, at A, the timer starts when the first bit starts its transmission. So the last bit is transmitted at time TT. TT is 500 microseconds, right? Which we have already calculated here. 5000 bits divided by 10 Mbps. But the last bit needs TP to reach S1. When the last bit is received, switch 1 needs T200 time only to transmit the last bit. Then that last bit needs TP. Similarly, S2 also, when it receives the last bit, it has already transmitted 4800 bits, so it has to transmit 200 more bits. So this continues. So the total time would be initial TT, this is TT, this is 4 times T200, 1, 2, 3, 4, then 5 times 1, 2, 3, 4, 5 TP, 630 microseconds. So cut-through switch also reduces the transfer time. Cut-through switches where are there are or where commercially available, not popularly used now, okay, but they were there. But it has other drawbacks. Okay, one important drawback is the error propagation. That means later we will see error detection mechanism and all. Right? We need all 5000 bits to detect the error. We need to use some function to see whether the bits are damaged. Any bit is in error or damaged. Okay, but if you start transmitting before you receive all the bits, if there is an error, you already propagated the error. Okay, or sent they are out. I mean, you already consumed bandwidth on the next link. Okay, so that's the key drawback of this. So generally switches now prefer or go for store and forward type. They don't do cut through. Okay? Though commercially the switches were there, cut through switches. Let me stop here. You have any doubts? Okay, students, we missed Monday class. I hope you all had a long weekend. Okay, nice holiday celebrations, New Year celebrations. I thinking of arranging some makeup lecture either on Friday or Saturday. I'm not getting the venue. I need a venue to conduct the, so I'm trying to book a venue. Okay. Once I book the venue, I will make an announcement for the makeup lecture. Okay, I try my best to conduct makeup lecture this week itself. If not by Friday, maybe Saturday morning. Maybe 10 to 11:30, 2 hours, right? 1.5 hours. Right? Friday or Saturday, please wait for my message. Okay? As usual, this will be recorded, webcast. That doesn't mean that you should be absent, right? You try your best to attend the lecture. Okay?